Alright, so this is chapter 4 and it's speaking about the metal casting process. Okay, so the contents we are going to cover would be introduction to the sand casting process, and then we are going to look into two types of casting. Alright, the expandable mold and the permanent mold. So we have the different casting processes under expandable mold, like shell molding, vacuum molding, expandable, polystyrene process, investment casting, plaster mold, and ceramic mold. And then under permanent, we're going to have slush casting, low pressure casting, vacuum permanent, die casting, squeeze casting, and centrifugal casting. Then we look at the quality of casting and the design considerations, all right, for casting process. And I'll show you a video, two videos on simulation. So as I said, this is a manufacturing process. And now, like what we discussed in chapter 1, we are looking at computer-aided manufacturing. So there are CAM softwares to simulate the casting process itself, and we'll look at robot application in metal casting. All right, so introducing the casting process. So this is a process. Let me get my pointer out. So this is a process in which metal, molten metal, right, flows by gravity or other forces, okay, into a mold, and then it solidifies into the shape of the mold cavity. Okay, so we have molten metal. This is actually metal casting process. So we have molten metal, right, which as you pour, obviously it will be moving according to the gravitational force, pull, and other forces, and then it enters the mold, it solidifies and takes that mold cavity. So the term casting also applies to the part made in the process. So sometimes the product that you get out of the casting process, you call it casting, okay? Bracket casting, this casting, like that, okay? So steps in casting, it looks direct, right? We first melt the metal, we pour it in, and then we let it freeze. So it's not as straightforward as that, okay? So, like I mentioned earlier, we have two types of casting. We have the expandable mold process, all right, which uses an expandable mold which must be destroyed or removed after the casting process. So the mold materials for this expandable mold will be sand, plaster, and materials similar to that, plus binders, all right, to bind this. For the permanent mold, we use a permanent mold which can be used over and over to produce many castings. So usually it's made out of metal, or less commonly a ceramic refractory material, okay? So this is like a what we call diagram, all right, for the casting process, whereby in general, okay, for a casting situation, other processes have other what we call functions, right? So for this sand casting, okay, under the sand casting process, you will see that you will have a pouring cup, okay, which is like, you know, in your sand, you dig out the shape, a tapered, drafted shape, okay, and then you have your down sprue where the material will flow down, okay, and then there is the runner, and there is a riser gap, okay, given over here for the metal to rise. Usually it will be notable from the top. And then you have your the shape, the cavity over here, okay? So you have the cavity shape over here, and this is what we call a core, this plug over here. So this core is given when you actually need a hollow shape within this particular formation that you're going to make, okay? Then there will be a parting line, all right, which divides the core, which divides the cope and the drag. So this is like the upper half and the lower half, and all these things will be packed within a flask, okay? So the mold itself basically is the sand in this case, all right? So sand casting mold terms, as I said, there will be the cope, which is the upper half of the mold, this, and the drag, which is the lower half of the mold, okay? Mold halves are contained in a box called a flask, and the two halves are separated at the parting line. So the pattern itself is a full-size model of the part, slightly enlarged, all right, to account for shrinkage and machining allowances in casting. Okay, so casted products usually do not have fine finish, right? And then you have the pattern materials which we use for the patterning. We have wood, common material because it is easy to work, but it warps, all right, due to external influences, okay? Then there's metal. It's more expensive to make, but it lasts us longer. And there's plastic. So this is a compromise between wood and metal. All right. Types of pattern used in sand casting. So we have the solid pattern, the split pattern, the match plate pattern where there is a plate in between, and we have the cope and the drag, okay? So what is the core used for? Like I mentioned earlier, the full-scale model of an interior surface of the part. It is inserted into the mold cavity prior to pouring. The molten metal flows and solidifies between the mold cavity and the core to form the casting's external and internal surfaces. So whenever you have an internal surface, then usually there will be the core to create that internal surface. So may require supports to hold it in position in the mold cavity during pouring. And these supports are called chaplets. Why do you need supports? All right, in case it tilts, all right, or shifts of direction. Okay, so the core in the mold, you can see over here, all right? These are the chaplets which is used to actually fix its position. So you have your riser over here, okay, the pouring cup, the down sprue, the runner, okay, the putting line, and this is the product. Hence, the outcome will look like this, okay? So the desirable mold properties, we are looking at strength. This is for sand casting. To maintain shape and resist erosion, okay? Obviously, when you pour something in, you must ensure that, you know, whatever molten metal, it's not going to erode your mold. Permeability, to allow hot air and gases to pass through the voids in the sand to allow the heat to escape, all right? Thermal stability, to resist cracking on contact with molten metal. And collapsibility, ability to give way and allow casting to shrink without cracking the casting. So it should be collapsible when you want to remove it. Forming the mold cavity itself. So mold cavity is formed by packing sand around a pattern, which has the shape of the part. When the pattern is removed, the remaining cavity of the packed and sand has the desired shape of the cast part. So the pattern is usually oversized, right? As I mentioned, enlarged earlier to allow for shrinkage of metal during the solidification and cooling. Sand for the mold is moist and contains a binder to maintain its shape. So basically for sand casting, the mold material, in general, they use binders, okay? So use of a core in the mold cavity, it provides the external surface of the cast part. In addition, a casting may have internal surfaces determined by a core placed inside the mold, okay, to define the interior geometry. So in sand casting, cores are generally made out of sand. The gating system, it's a channel through which the molten metal flows into the cavity from outside the mold. It consists of the down sprue, in which the metal enters the runner and goes into the cavity. At the top of the down sprue is a pouring cup. Okay, as I said, it's a cup like this, which is tapered. Okay, and why is it a tapered cup? Naturally, when you pour something, a taper allows, you know, the rise of the, you know, when you over pour, okay, the spillover. Okay, it's not too obvious. To minimize the splash, a pouring cup, right, is often used to minimize the splash and turbulence. So this is another reason why it is tapered, okay, as the metal flows into the down sprue. So you have to take note that the metal that's being poured is, number one, molten metal. Hence, you can imagine when it splashes on you, all right? Then there is the riser, okay? So this is the riser. Over here, this is the riser. It's a reservoir in the mold, which is a source of liquid metal to compensate for shrinking of the part during solidification. The riser must be designed to freeze after the main casting in order to satisfy its function. So basically, every molten metal that has been poured in has to freeze, okay? Heating the metal. Heating furnaces are used to heat the metal to molten temperature sufficient for casting. Heat required is the sum of heat to raise temperature to melting point, okay? So our last week's chapter, we spoke about forging. So in forging, we actually raised the temperature to half of the Tm, all right, of the melting point. So you don't want a melting point, because a melting point is, in general, if you look at the material graph, right, we have the elastic region, then you have the yield point, then you have the plastic region, and then you have the fracture point. So we use this plastic region when we want to do metal formation process. But when we want to completely change the nature of the metal, then melting point means, to an extent, though of course it does not indicate fracture. We don't say there's fracture in liquid, all right? The point is the complete shape, bonds, everything, they are broken in order to create the formation. So heat of fusion to convert from solid to liquid, heat to raise molten metal to desired temperature for pouring. So for this step, when we want to pour the molten metal, to be successful, metal must flow into all regions of the mold, most importantly the main cavity, before solidifying. So what determines the success? The pouring temperature. So I said it has to be melted enough and melted slightly more. The rate of pouring, if it's too slow, then the solidification starts taking place. We want to ensure there is no turbulence, because when there is turbulence, then you start capturing air holes or pockets, which will later increase or create porosity and create defects. Solidification of the metals, transformation of molten metal back into its solid state. Solidification differs depending on whether metal is a pure element or an alloy. Of course, that's how it returns back to its shape. So the time taken for solidification, right, Ts, is the time required for casting to solidify after pouring. And it depends on the size, shape of casting, all right, by a relationship of what we call the Shvorinov's rule, all right? So the Shvorinov's rule is such that you have your solidification time, all right, which is equals to your mole constant times, all right, the volume of the casting. So when you say the volume of the casting, that means the product over the surface area of the casting, and to the power of an exponent, okay, which usually has a typical value of 2, which has been standardly set, okay. So in the Shvorinov's rule, the Cm, so what is the Cm over here? It is the mole constant. So the mole constant depends on the mole material, thermal properties of the casting material, metal, and pouring temperature relative to the melting point. So the melting point is 350, and then so you have your pouring temperature, okay, which is slightly higher, so that you will allow the cooling to take place. So value of Cm for a given casting operation can be based on experimental data from previous operations carried out using same mold material, metal, and pouring temperature, okay, even if you're using a different shape. So what does this rule tell us? A casting with a higher volume to surface area ratio cools and solidifies slower than the one with a lower ratio. So to fit molten metal into the main cavity, right, the solidification temperature for the riser must be greater than the solidification temperature for the main casting, okay. So the solidification temperature for the riser, we have the pouring cup, okay, and then the down sprue, and then you have the runner, and then you will have the riser over here, okay, and then after that it goes into our pattern, okay. So the temperature at the riser over here must be greater than the temperature for the main casting, basically, okay. It solidifies first, then desolidifies next. The mole constant of riser and casting will be equal. Design the riser to have a larger volume to area ratio so that the main casting solidifies first, as mentioned earlier. So this will help minimize the effects of shrinkage, okay. So the shrinkage in solidification and cooling. So when you pour something, of course, you have the equal level. When it shrinks, the level will dip, okay, based on the contraction of the liquid. Reduction in level caused by liquid contraction during cooling, okay, which reflects the dimensional reduction Okay, so this is basically exaggerated over here to show you the clarity of what happens. So in a casting process, this is usually not very obvious to our naked eyes. So the reduction in height and formation of shrinkage cavity caused by the solidification shrinkage. So when you have a shrinkage cavity that forms inside, so you have your molten metal, all right, and your solid metal, further reduction in height and diameter due to thermal contraction of cooling during solid metal. Dimensional reductions, okay, these are exaggerated again. So you're not going to get this kind of reductions, all right? Not to say not get this kind of reduction, but as I said, it will not be obvious to the eyes directly, okay? But this is the image to actually show you when there is a shrinkage occurring. So our shrinkages in casting will never be this large, all right? But nevertheless, it will be there, okay? And when it is there, as I said, they are defects which lessens the structural integrity. So solidification or shrinkage occurs nearly in all metals because solid phase has a higher density than the liquid phase. Thus, solidification causes a reduction in volume per unit of weight, all right? Exception, cast iron with high C content. So graphitization during final stages of freezing causes expansion that counteracts the volumetric decrease associated with the phase change. So this is an exception of cast iron due to the high carbon content, all right? So due to the high carbon content over here, this graphitization process, okay, which takes place towards the end of the freezing, right, actually expands. Basically, the graphitization creates expansion. Hence, it makes up, all right, for the decrease in volume when shrinkage happens. So they become like the same in the end. Shrinkage allowance, pattern makers account for solidification shrinkage and thermal contraction by making mold cavity size oversized. Not oversized as a huge oversize. There will be an allowance and tolerance value for this. Amount by which mold is made larger relative to final casting size is called the pattern shrinkage allowance. Casting dimensions are expressed linearly, so allowances are applied accordingly. Okay, then we have the riser design. So it's a waste metal that's separated from the casting and remelted to make more casting. To minimize waste in the unit operation, it is desirable for the volume of metal riser to be minimum, yet sufficient enough to ensure that the solidification process occurs properly. Since the geometry of the riser is normally selected to maximize the the volume over area ratio, this allows the riser volume to be reduced to the minimum possible value. Okay, so now we are going to go into different expandable mold casting. So in sand mold casting itself, the concept of solidification was described. So this concept is applicable across all other casting procedures. So this is one thing we need to understand. The shrinkage factor that takes place is also described here, all right? And this being the sand casting layout schematic diagram. So the other diagrams are different, all right? But in all forms, all right, there should be a situation where you have permeability, okay? You have all these functions, all these factors taken into consideration, all right? The thermal stability, the collapsibility. So the collapsibility is important in any expandable mold casting, all right? The thermal stability is important for all castings. Permeability must be there as well. Of course, this is in sand casting or expandable casting, but in permanent casting, it works in a different manner, all right? It fills up the cavity correctly, and the strength has to be there. Okay, so I will show you a sand casting video before we move on into expandable mold. Wait, why is this not opening?
Sand casting. Sand casting is the
Okay,
most
there should be volume. So in case there's no volume, let me know.
widely used casting process in manufacturing. The advantage of using sand to manufacture products of metal is that sand is very resistant to elevated temperatures. Almost all metal casting materials can be sand cast. Sand castings can range in size from very small to extremely large. Some examples of items manufactured in modern industry by sand casting process are engine blocks, machine tool bases, cylinder heads, pump housings, and valves.
So a lot of automobile parts, right? The internal engine parts are used made
Now
out
we
of
will
sand casting.
understand the process of sand casting in detail. First of all, on a clean floor, we will set the inverted drag box. Then we will place the pattern inside the box and pour the sand into the box. After that, sand is rammed and leveled off. The packed drag box is then turned over and cope box is placed over it. After that, second half of the pattern is placed exactly over the first half of pattern. Then the sand is filled and rammed tightly. Now two boxes are opened and pattern is removed with the help of screws. Boxes are again put back into position and clamped with rivets to prevent upper box floating. Gates and spruces are formed to pour the metal. Now the molten metal is poured into the mold. Then it is allowed to cool down for some time. After cooling, the final cast is taken out.
Okay, so that is for sand casting. So now we move into the first expandable mold casting, which is shell molding. Okay, so shell molding. So this is a casting process in which the mold is a thin shell of sand held together by thermosetting resin binder. So you have your sand, which is like the resin binder, a dump box, which is like a flask over here, and then you have your pattern, and the pattern is heated to such an extent that when you overturn the pattern, all right, the box is inverted so that the sand and resin fall onto the hot pattern, causing a layer of mixture to partially cure on the surface and form a hard shell. So the box is repositioned so that loose uncured particles drop away. Okay. And then the sand shell is heated, all right, in an oven for several minutes to complete the curing. So basically it's like baking, you're just firming the thing up. And the shell mold is stripped from the pattern. Okay. What happens later will be the two halves of the shell mold are assembled, all right, supported by sand or metal shot, all right, in a box. And you pour the molten metal in. The finished casting with the sprue is then removed. Okay, so this is basically shell molding. The pros and cons. You get a smoother cavity surface, all right, which permits easier flow of metal, molten metal, and better surface finish compared to sand casting. Better dimensional accuracy. Machining is usually not required. Collapsibility of the mold minimizes crack in the casting and can be mechanized for mass production. The cons, it's more expensive metal pattern and difficult to justify for small quantities when you're using shell mold casting. Okay, so that shell mold casting.
studying fundamentals of metal casting and metals for casting. We will cover all related topics one by one. Before starting, there are other casting processes that have been developed. The composition of the mold is a thin shell made of sand held together by thermosetting resin binder. Was developed in Germany in the early 1940s. We are going to observe the steps of shell molding in the next few figures. The figure 1 shows the first step in shell molding, where a match plate or copen drag metal pattern is heated and placed over a box containing sand mixed with thermosetting resin. The figure 2 shows the second step in shell molding, where the box is inverted so that sand and resin fall onto the hot pattern, causing a layer of the mixture to partially cure on the surface to form a hard shell. The figure 3 shows the third step in shell molding, where the box is repositioned so that loose, uncured particles drop away. The figure 4 shows the fourth step in shell molding, where the sand shell is heated in oven for several minutes to complete curing. The figure 5 shows the fifth step in shell molding, where the shell mold is stripped from the pattern. The figure 6 shows the sixth step in shell molding, where the two halves of the shell mold are assembled, supported by sand or metal, shot in a box, and pouring is accomplished. The figure 7 shows the seventh step in shell molding, where we can see the finished casting, with sprue removed. There are many advantages of shell molding. The surface of the shell metal
Okay, so I'm not going to
camshaft.
show you. All right. So parts made,
So,
gears,
we have studied
camshaft.
shell molding, which is one of the expandable mold.
Okay. All right. Next, we move to, where's my mouse? All right. We move to expanded polystyrene process. Okay. So this uses a mold of sand packed around a polystyrene foam pattern. All right. So the pattern is made out of polystyrene foam, which vaporizes when the molten metal is poured into the mold. So you know polystyrene foam, obviously, it's not heat resistant, right? So that's the whole idea. The foam pattern is put in and packed around with sand. And then you pour in the molten metal, and that causes the polystyrene to vaporize. So other names is what we call lost foam process, lost pattern process, evaporative foam casting, and full mold process. So these are other names for this expanded polystyrene process. So polystyrene foam pattern includes sprues, risers, gating system, internal cores if needed, similar to sand casting. Mold does not have to be open into cope and drag sections. Okay, so you have your cup and sprue foam, the foam pattern, and you're spraying some refractory compound. So these are some shapes, all right, that can be obtained out of this lost foam process. Pros and cons. Smoother cavity surface permits easier flow of metal, right? Better surface finish, good dimensional accuracy, no machining required. Mold collapsibility, similar to shell mold, minimizes crack. You can also mechanize. The disadvantages are pretty similar to the shell mold. Sorry. What am I saying? Sorry, I was mistaken. Okay. Now, expanded polystyrene process. Okay, so once you put in the polystyrene pattern, okay, so this is the polystyrene pattern. This is packed with sand. All right, and then you have your mold box, which is like the flask. Okay, and then you pour in your molten metal into this. Okay, so what happens is, as I said, it vaporizes this and takes over this shape. Okay, now these are the pros and cons. Pattern need not be removed because it naturally vaporizes. It simplifies and speeds mold making because two halves of the molds are not required to remove and add. Okay, these are the pros. Cons. New pattern is needed each time you want to cast. Economic justification of the process is highly dependent on the cost of producing patterns. And to add on, I also would like to, to add on, all right, the smoother cavity surface also permits easier flow of metal and better surface finish. So this particular advantage is applicable to lost foam, all right. Dimensional accuracy is also applicable to lost foam, all right. Mold collapsibility, all right. is also applicable. So it's not that your mold collapses, your mold, it is not mold collapsibility, it is pattern collapsibility. Okay, for loss foam, the pattern collapsibility minimizes cracks in casting. Okay, so those factors are can be incorporated here as well. The process itself, all right, the applications, mass productions of castings of automobile engines, automated and integrated manufacturing systems are used to mold the polystyrene foam and patterns, then feed them to the downstream casting operation. So, okay, the next one is we are going to investment casting. So I will give you the video of expandable mold. We'll look at vacuum molding first.
Welcome to Academic Gain Tutorial. We are studying scribe and except or the manner of vacuum molding in the next few figures. The figure 1 shows the first step in vacuum molding, where a thin sheet of preheated plastic is drawn over a match plate or cope and drag metal pattern by vacuum. The pattern has small vent holes.
Let me see. Hang on. All right, okay. So you will look at the, okay, we can look at the vacuum molding video.
To facilitate vacuum forming. The figure 2 shows the second step in vacuum molding, where a specially designed flask is placed over the pattern plate and filled with sand, and a sprue and pouring cup are formed in the sand. The figure 3 shows the third step in vacuum molding, where another thin plastic sheet is placed over the flask, and vacuum is drawn, that causes the sand grains to be held together, forming a rigid mold. The figure 4 shows the fourth step in vacuum molding, where the vacuum on the mold pattern is released to permit pattern to be stripped from the mold. The figure 5 shows the fifth and final step in vacuum molding, where the mold is assembled with its matching half to form the cope and drag, and with vacuum maintained on both halves, pouring is accomplished. The plastic sheet quickly burns away on contacting the molten metal. After solidification, nearly all of the sand can be recovered for reuse. Advantages of vacuum molding. Since no binders are used, sand recovery is almost a perfect process. The sand does not require extensive mechanical reconditioning normally done when binders are used in the molding sand. Since no water is mixed with the sand, moisture-related defects are absent from the product. Disadvantages of vacuum molding are: it is relatively slow, not readily adaptable to mechanization. So, we have studied vacuum molding, which...
Alright, so in the notes just now, vacuum molding was not inserted, okay? So I'm going to use the video itself, alright? So this is a relatively later process, okay? Whereby what we have is a thin sheet of preheated plastic, alright? Which is drawn over a match plate, alright? So when we talk about match plate or cope and drag, so early on this were the pattern, types of pattern, right? We use in sand casting that was shown, alright? So either a match plate or a cope and drag metal pattern, okay? By vacuum, the pattern has small vent holes to facilitate vacuum forming, okay? And then
forming. The figure 2 shows the second step.
Then you have a specifically designed flask, all right, which is placed over the pattern plate, okay, and filled with sand and a sprue and a pouring cup, all right. So basically this is something like a mixture of shell molding and sand casting, okay. So you have your flask over here and then you have your sand, okay, compacted.
Step in vacuum molding, where a specially designed flask is placed over the pattern plate and filled with sand, and a sprue and pouring cup are formed in the sand. The figure 3 shows the third step in vacuum molding, where another thin plastic sheet is placed over the flask, and vacuum is drawn, that causes the...
So the whole idea over here is to vacuum that entire structure in such a way you compact your mold. Okay, so once the mold is compacted, then the same process. You pour in your molten metal, your plastic sheet will evaporate with the heat, you form, and then
the sand grains to be held together, forming a rigid mold. 4 shows the fourth step in vacuum molding, where the vacuum on the mold pattern is released to permit pattern.
Okay, so how do you exactly release this? You release the vacuum pressure. So therefore, it will release it from the mold. And you can obtain your...
to be stripped from the mold. The figure 5 shows the fifth and final...
Okay, so you can remove your pattern and then compact it back again, all right? And the vacuum is maintained, okay, so that you get your final full compaction, and then you pour your metal in, okay? So we will add this in, okay? So this was left out, and then the other one is expandable polystyrene process.
Welcome to Academic Gain.
Nickel electroplating.
Welcome to Academic Gain Tutorials. In today's and metal at, just click on. Except sand casting, there are other casting processes that have been developed to meet. Position of polystyrene process uses a mold of sand packed around a polystyrene. Also, polystyrene pattern includes the sprue, risers, gating system, and drag sections. We are going to observe the steps of expanded polystyrene casting process in the next few figures. The figure 1 shows the first step in expanded polystyrene casting process, where pattern of polystyrene is coated with a refractory compound, in order to provide a smoother surface on the pattern and to improve its high temperature resistance. The figure 2 shows the second step in expanded polystyrene casting process, where foam pattern is placed in mold box, and sand is compacted around the pattern. The figure 3 shows the third and final step in expanded polystyrene casting process, where molten metal is poured into the portion of the pattern that forms the pouring cup and sprue. As the metal enters the mold, the polystyrene foam is vaporized ahead of the advancing liquid, thus allowing the resulting mold cavity to be filled. Advantages of this process include pattern.
Okay, so we already discussed the advantage earlier. All right. So the next one is, okay, investment casting, all right, or lost wax process. So a pattern is made of wax. A pattern made of wax is coated with a refractory material to make the mold, after which the wax is melted away prior to pouring the molten metal. So investment comes from a less familiar definition of invest, to cover, or which means to cover completely, which refers to coating a refractory material around a wax pattern, okay? So it's a precision casting process capable of producing castings of high accuracy and intricate details and fine finish, okay? So you have your wax pattern over here, okay? So you have your wax pattern produced, and several patterns are attached to a sprue to form a pattern tree. So you can actually have multiple formations over here, okay? Then this entire pattern tree is then coated with a thin layer of refractory material, okay, dipped into a refractory material. The full mold is formed by covering the coated tree with sufficient refractory material to make it rigid. So you dip, you take out, it solidifies, you dip, you take out, it solidifies. So it's like in, out a few times until you get a layer like this, okay? Then the mold is held in an inverted position and heated, all right, to melt the wax and permit it to drip out of the cavity, okay? So once that happens, all right, the molten metal is preheated and poured into the mold, and we wait for it to solidify, okay? So once it solidifies, okay, the mold is broken away from the finished casting and parts are separated from the sprue. So these are examples of parts. Pros and cons. Parts of great complexity and intricacy can be made. Dimensional accuracy, dimensional accuracy and close tolerance and allowance control is good. Surface finish is smooth. Wax can usually be recovered, okay, for reuse of this entire process. Additional machining is usually not required because we get usually a net shape product. The cons, many processing steps are required, and this is generally a relatively expensive process. Okay, so we will look at investment casting now. So the wax patterns are produced using metal injection molding. So you need multiple patterns of this. We assemble the pattern, all right, on the pattern tree. We coat it with refractory material, all right, the slurry coat we call it. So repetitive coating, all right. So this refractory material is one which can actually resist. So the whole idea over here, early on, is what I said, all right. We actually form a wax method by using the MIM metal injection molding method. Assemble in the tree. Okay, we fit in the slurry or refractory material again, in and out. Okay. And we have a few layers of it to allow some thickness to form. Okay, and this particular few layers. So you actually melt the wax. Now you turn the tree upside down and you melt the wax, okay, by imposing heat. So when the wax comes out, you will get a cavity in this pattern. Obviously not pattern, but the slurry coat. Usually you take this out either through vibration, right? Okay. Okay. So that's for investment casting. Okay, so then we have plaster mold casting. So this is similar to sand casting, except mold is made out of plaster of Paris, all right? We call this gypsum. Okay, so this is the chemical composition. In mold making, plaster and water mixture is poured over plastic or metal pattern and allowed to set. So wood patterns are not generally used due to extended contact with water. In plaster mold, your pattern, generally you don't use wood because there is involvement of water, whereas in sand casting, there is no water involvement. Plaster mixture readily flows around the pattern, capturing its fine details and good surface finish. So this usually gives a better finish than sand casting. Pros and cons. Good accuracy and surface finish for the pros. Capability to make thin cross sections. Cons. Mold must be baked to remove moisture, which can cause problems in the casting. Mold strength is lost if it's overbaked. Plaster molds cannot stand high temperature, so it's limited to alloys with lower melting points. Okay, I'll just go through this. Ceramic mold casting. So this is similar to plaster mold casting, except that mold is made out of refractory ceramic material. Okay, that can withstand higher temperatures than plaster. Can be used to cast steels, cast irons, and other higher temperature alloys. Application is similar to plaster mold except for the metal cast. So the advantages are also similar. So for today, I will only stop with expandable mold. Next week, we will go on to permanent mold. So I will show you all the video. Mold.
So for safety reasons, the first thing that we need to do is remove things, get them ready to cast plaster Paris as well. So originally I was thinking on showing you how to cast polyester resin, which at the end is the exact same method, but I just don't want to waste too much resin right now. This volume is too big. So just for practical purposes, to show you how to prepare molds and cast liquid into a mold, I will do it in plaster Paris. So as I said, the process is exactly the same no matter what are you casting. First of all, we need to prepare the molds with wax. Same thing as before, put one layer of wax, let it dry, and then remove excess, and then repeat. Put wax, let it dry, classic hand wash soap with a little bit of water that I will use for the final zone where the liquid will go in, but also around here, because you never know when some of the liquid will flow into the union of the two molds, and that will get our molds glued together. So we have to do all this, and the cone for pouring in the material, and that's pretty much it. Then it's preparing the material, preparing the plaster in this case, and just pouring in it. So that's it. Let's do it. Added so I finished the wax layers, and I also added the soap layer, the watery soap. So that's it, we're ready. I close the molds with a string. You can use elastic, you can use edge somewhere here. So if that happens, you can always use a little bit of plasticine and try to block it. More
This is it
plasticine
seeps out
before
of the
you pour it in all around. I have here my plaster. This is the powder. The specific brand that I'm using. Just mix well and pour it, and hopefully everything will be good. So you may have noticed I didn't fill the whole cavity. I'm always super extreme with the wasting of material. I don't want to waste material, so I'm normally short. That's what happens. But it's okay because it's not. And the other bit that I'm going to probably see a line of the union between these two, and the union is never going to be as good as. So I'm going to pour a little bit more in. There we are. Mixing well. Remember to get rid of all of the leakage. I think I'm ready. It's has hardened. So I had to do a second mix of material and added it, but this time it was too much. So this is exactly what I want to avoid, waste, but I still wasted. So an important thing that I always tell my students, and there is always one that or do not get it or doesn't want to pay attention. So when you mix, obviously the bucket is going to get dirty with plaster. If you pour the entire contents of your bucket, there is no more plaster in the bucket other than the plaster that gets gets stuck in the walls and in your hand. That you can clean your bucket with plenty of water in your sink. As long as you have plenty of water, the plaster will dissolve and can flow through the pipes without problem. As long as it's just what is dirty in the walls of the bucket, and wait until it's thing of plaster into plaster is not thing worked. So I need to. Okay, there it is. And just like before, don't stress yourself. Let's hope that this didn't get stuck. It seems that it did. I'm gonna bring my mallet, just like the time before. Wait. So it was rough, but I made it. It came out. I had to break a little bit of the model in order to make a lever and leverage and pull it out. This can be fixed with more plaster, and you can just sand this and have a nice finish, and it works. It works. Now the reason why it broke, you can see it here how it broke. That's just in a little corner. It's not important. But this is the interesting bit. When I was taking this out, it broke like this. So what it means is that this type of broken piece is that the mold had a negative angle. So when I extracted the piece was, the mold was over the piece. So when I extracted the piece, the object was on top of, the mold was on top of the piece. So when I extracted the mold, the mold broke. Mold flat surface here. Dividing this into mold may be not the best idea. It may be better to divide it in 3 or 4, or maybe more pieces, different partition.
Okay, so all right, so that was plaster mold casting. Okay, so as I said, wood patterns are generally not used due to water. Okay, and plaster mixture readily flows around the pattern, capturing the fine details. Okay, so we mentioned this already. Okay, so we are somewhere about half of the chapter. The other half is actually permanent mold casting. Okay, so which is not too much, right? So we will work on this the next week. Okay, so do you all have any questions so far? So this is pretty direct, so you can rewatch these videos to understand. Okay, and these are your fascias. Okay, so this is the one which I have uploaded into UFuture. Okay, so what you can do now Okay, you can see these are some of the questions. I'm going to go from the bottom because this is taken from the latest. So die casting is a method that can be used to produce automotive components. Discuss the advantages of this process compared to sand casting. So this you will learn in permanent mold. So next week. Investment casting is a method that can be used to produce automotive components. So this is direct, the advantages, the disadvantages, all right, compared to sand casting. So the advantages of investment casting, you can get multiple products, the surface finish is smoother, okay, you can get more intricate details, all right, in comparison to sand casting. So like that, you can give your advantages. So this is a casting process again for automotive products. Illustrate with explanation the best process to produce automotive clutch transmission housing made from aluminum alloy as shown over here. All right. So explain the sequence of the process. So can you all give me your suggestion? What process do you think this particular product will go through? Anyone? Flip back on your notes. Okay. I'm not looking at the permanent mold yet. Okay, so wait. Okay, the thing here is, okay, since you all do not know die casting yet, so that's fine. All right, never mind. I'll skip this question. Okay. How do you overcome each problem listed below in order to maximize castability and casting consistency? So we have the shrinkage stresses. We saw that in expandable mold, okay? And then you have distortions, you have concentration, so this will be there in the permanent mold. So we have to look through. Okay, never mind. Let's just see if there's anything directly on expandable. Okay, so these are questions based on sand casting alone. So what are the functions? So you should be able to, usually sand casting questions are very popular because the schematic diagram is almost something that we should memorize almost, okay? So that you should know, okay? Explain what is shrinkage. Okay, discuss advantages and disadvantages of casting process over other manufacturing process such as machining, forging, stamping, okay? So this is not so direct, but it's for you to cross contrast. So these are the things you can work upon, okay? So now I want to ask you all, anyone with any questions?